Good afternoon, everyone. Welcome to the next talk. My name is Asokan, and I'm going to be giving this talk along with my colleague Lachlan Gunn. We're going to be co-presenting this talk. We are both from Aalto University in Finland. So the talk is about deniability in messaging protocols and how that is circumventable using attestation. And the attack that we are going to describe is the result of a convergence of two major trends. The first one is that hardware-based so-called trusted execution environments are pervasively deployed. The second one is that the popularity of deniable communication and the demand for deniable communication in messaging protocols or messaging apps has risen dramatically. So what I'm going to do is to explain these two trends first. What are TEEs and what do I mean by remote attestation? And then we'll talk about what is deniability, what does it mean to have deniability in messaging protocols. And then Lachlan will take over, tell you about how is deniability achieved in today's messaging protocols, and then show you how the widespread deployment of attestation can break deniability guarantees in messaging protocols. Unfortunately, we can't do a demo because we had presentation issues, but we'll show you a video. If you want to see a live demo, go talk to Lachlan after the talk. We can do the demo on his machine. Then we'll talk a little bit about countermeasures and close with the big picture. So let me start with trusted execution environments and remote attestation. So what do I mean by this? Hardware security mechanisms in commodity devices have been gradually becoming more and more pervasive. What I mean by this are hardware support for three kinds of security functionality. The first one is something that I would call isolated execution environment. So imagine that you have a phone with, say, Android or iOS running on it, and you have all kinds of applications. All of this is software with a big footprint, right? So this is what we call sort of other software. If there is hardware support to be able to run small pieces of so-called trusted software on the same device, on the same processor, in such a way that there is strong isolation between these two, that the trusted software cannot be manipulated by or interfered with by this other software, including the operating system, that is called isolated execution. And there are hardware devices that support isolated execution environments and that are widely deployed. The second security property that hardware can support is it's nice to be able to run some software that's isolated from everything, all the other software on your device, but to be able to do something useful, imagine that you want to do online banking, this trusted software has to have some information like cryptographic keys that can be stored persistently, right? So this is called protected storage, and sometimes it's called sealing. So the trusted software is able to take something like a cryptographic key, seal it, and store it in such a way that even though the other software has access to that, the other software won't be able to manipulate that or extract this information without being detected by the trusted software. So that's the second property. The third property is that suppose you have a device that has isolated execution, that has protected storage. Imagine that if this device is now able to convince a third party that it has these properties, then the third party may be able to use simpler protocols, right? So imagine that you want to do online banking, and you have a device that supports this kind of the ability to run some software in an isolated fashion, the ability to protect secret keys, and now your device can convince your bank that it has this functionality. Then maybe your bank would allow great access to your bank account from such a device than from a purely software implementation. So this kind of support in commodity devices have been around for a while, starting with, say, IBM crypto cards that are almost 30 years old that were used in the banking sector, or trusted platform module, which were about 20, 25 years old, that have been sort of reasonably widely deployed on PC-type platforms. But what's interesting in the last 15 years or so is that in common hardware, such as smartphones, tablets, PCs, cloud platforms, this kind of support for trusted execution environments have been widely deployed. So if you have a smartphone in your pocket today, it's probably made by using an ARM-based core, And ARM has a technology called Trust Zone that provides this kind of trusted execution environment. And such trusted execution environments in smartphones and tablets have been around for almost 15 years. Intel recently announced a technology called software guard extensions that provide similar functionality for x86 platform. So the fact that these are widely deployed allow developers and system builders to design interesting new protocols which can provide the kind of security that wasn't previously possible if you were using only software-only mechanisms. So this is why trusted execution environments are interesting, and like I said, it has been widely available. So what is remote attestation? So I mentioned briefly earlier that if your device has a trusted execution environment, and if you can convince a third-party remote verifier of this functionality, then they'll be able to do more interesting things than they could do before. So remote attestation is essentially a verifier being able to assert the current state, such as whether there's a trusted execution environment or not, what kind of application is running in the trusted execution environment, and possibly also the behavior of this trusted software on the prover device. And there are essentially two parts in a remote attestation process. The first one is that on this prover device, where there is such a trusted execution environment, you should be able to characterize this current state, right? So this is called the measurement process. So somehow you measure the current state. And the second part is that the evidence that you gather from this measurement process has to be securely conveyed to the verifier. And this is the attestation protocol, right? And you can imagine the kind of properties that are needed for an attestation protocol. So first of all, you need authenticity, so that the evidence that's gathered from the device and sent to the verifier should be secure, even in the presence of an adversary who is controlling the communication channel. And that suggests that you need to be able to have some way of signing this evidence, this measurement that you collected on the device. And that immediately suggests that there should be some kind of certified key that is available to the trusted execution environment, and that's certified by some party that's trusted by the verifier, right? It may be the manufacturer of the device, or it may be some third party. Furthermore, in order to use this key securely, that key should be available to some kind of trusted computing base on the device. This is sometimes called the root of trust. And the root of trust, the rest of the trust is built from having trust in the trusted computing base in the first place. The second property that might be needed for a attestation protocol is a verifier might want to know not only that the prover device has a trusted execution environment that matches certain properties, but also that that property holds right now and not sometime in the past. This is not always necessary. As you will see in our attack, that's not an essential protocol. But whenever you need this kind of timeliness guarantee, essentially you do this by having a nonce included in the challenge that the verifier sends to the prover, and having the prover include that challenge in the response that they send back. So an attestation protocol works in the following way. So the verifier has some idea of what are acceptable configurations for a given prover device, right? So this is prior knowledge for the verifier. The prover device, like we said, has a key that can be used for attestation. The key is certified by somebody who the verifier trusts, and that key is available to this root of trust that's going to do this measurement of whatever property that you want to prove to the verifier. So at some point, when maybe during device boot or during a process launch, this measurement process happens. So the root of trust will measure whatever the information that you want to prove to the verifier. At some later point, the verifier wants to know if the prover device is in an acceptable state. The verifier might send a challenge. The prover would then take this challenge, combine that with the measurement, sign that using this attestation key, and send this information along with the certificate with this attestation key. So the verifier would check the signature, check the certificate, but on top of that, he has to also check that the measurement that was sent securely by the prover is an acceptable measurement. Right? So typical attestation protocols work like this. So the notion of attestation was introduced by Trusted Computing Group in the context of trusted platform modules about 2 decades ago. And like I said at the beginning, what is more interesting is that trusted execution environments supporting remote attestation are now widely available in smartphones, in PC platforms, in server-grade platforms, and so on. And the fact that they are available is good in some sense, because you can have, for example, secure banking and all kinds of interesting protocols that provide better security than before. What we're going to show here is that how it might be used in a negative way. I talked about measurement or gathering this evidence. Typically, the measurement is you want to prove to verify that you are running a process that was started from a specific application. And the measurement is then called a binary measurement, a binary attestation, and essentially it's taking a cryptographic hash of the binary code from which you started the process. But the notion of attestation is general. It doesn't have to be just binary attestation. It can be of any kind of property. And one other thing that I want to mention is that the attestation can also be chained. So for example, if you're testing an application, you will take a binary hash of that application code from which you're going to start the process, but you can add other things. For example, the application might make some statement about some property, right? Some data that it produced as a result of running some computation. So in addition to the measurement of the code itself, you can include this additional data, and that amounts to saying the verifier being convinced that not only is the prover or is running a certain application, but also the application uttered some statement as a result of some computation. And there are different ways of doing this kind of additional information to the attestation. And you'll see later how this can be used. So this is what I want to say about attestation. And if you want to sort of take one thing away from this brief introduction, that is the following. If there is a way for a trusted execution environment to locally verify some property, such as the signature of an application, attestation allows a way for this trusted execution environment to securely convey this property to a remote verifier. So anything that can be locally verified, now you can use that to convince a remote party. So that's about attestation. Now let me tell you about this deniability in messaging protocols. So if you think about any messaging protocol, like if you're using Signal or WhatsApp or whatever, the natural security requirement that you would want to have is the ability to authenticate the source of the message that you receive, right? So if I'm communicating with Lachlan using WhatsApp, he sends me a message, I want to know that it was really sent by Lachlan and not somebody who broke into our communication, right? Deniable messaging protocols do provide authenticity, but they have this additional property that even though I can verify that a message came from Lachlan, I'm not able to convince any of you that Lachlan sent this message. So I want authenticity, but he wants that I shouldn't be able to convince anybody else that he sent me a message. So what you want is to any third party to be able to not differentiate between a message that the actual sender sent and a message that somebody fabricated. And typically, deniability is provided by ensuring that there is sender authentication, but after the fact, anybody can produce a transcript that looks like the genuine transcript. And a third-party verifier won't be able to tell the difference between a genuine transcript and a fabricated transcript. And Lachlan will later show you how this is done. So Signal, WhatsApp, Pigeon, and many of these modern messaging protocols do support deniability in this sense using cryptographic mechanism, right? So this is sort of widely available these days. So what is it that you can achieve if you are using a cryptographically deniable protocol, right? So you can imagine why you would want to do that, right? If you are a whistleblower who wants to talk to a watchdog or a journalist, and you want to tell them about something that might land you in trouble, you might want to use a protocol that provides authenticity so that the journalist can verify that it's you really who's saying this, but they won't be able to out you or frame you in any way, right? So suppose Alice is such a person who wants deniability, and she's talking to Bob, and she's using a cryptographically deniable protocol, right? And Alice might say things that are potentially incriminating to her, and might believe that because the protocol is deniable, Bob won't be able to take that message and send it to some external verifier, like publishing it in WikiLeaks dump or publishing it in a newspaper, and an external verifier, which could be anybody, wouldn't be able to trust this transcript that Bob produced because anybody could have produced that. But this is not necessarily always the case, right? So the verifier, of course, wants to know whether Alice really said what Bob claims Alice said. But even if you are using a cryptographic deniable protocol, if the verifier trusts the reporter, which in this case is Bob, then it wouldn't matter whether Bob could have fabricated or not, right? So if I trust Lachlan and Lachlan tells me that Alice said something to him, then I might believe that regardless of whether they use a cryptographic deniable protocol or not, right? So the use of cryptographically deniable protocol is relevant only when the informant who is taking this transcript and trying to convince some verifier is somehow inherently not trustworthy. So there are lots of trustworthy informants, right? So if you're a witness under oath, people might believe what you say because you are a witness under oath, and there are other ramifications if you lie. So even if somebody was using a deniable protocol to talk to you, if you under oath claim what they said, that you are reporting what they said, verifiers might believe that. Journalists might be such trustworthy reporters as well. But not everyone is such a trustworthy reporter. For example, there could be a nation-state adversary who takes email dumps from breaking into somebody's device and publishes them, right? So there is no reason to suspect that this nation-state adversary wouldn't have fabricated the evidence. So this is the kind of setting where deniable protocols are useful because the party that's taking the transcript of your conversation with them is essentially inherently untrustworthy from the point of view of a verifier. And this is, as you have probably seen from news reports and so on, the context for this is increasingly common, right? There have been all kinds of email data dumps or other kinds of data dumps that have been in the news in the past 2 or 3 years. Some of them successfully, some of them unsuccessfully, but all of them have this kind of setup where you or somebody was having a conversation with somebody else in the belief that it's a private conversation, but then it became public, right? And the reason why this is questionable is if the person who is making this information available can fabricate the evidence, then your conversation is essentially deniable. So even if you use a cryptographically deniable protocol, the messages that you send in themselves might contain some evidence that reveal the proof of origin. So a good example is what happened during the US elections, in the last US elections. So somebody broke into the campaign chair of Hillary Clinton and revealed a whole bunch of emails that he received from a bunch of people, right? So initially, the reaction of the senders was to claim that they didn't actually send this purported email that came from them. But WikiLeaks, who published this dump, shortly after these denials, they published the DKIM signatures on those emails. And that essentially served as proof that those people who claimed that they didn't send the mail actually did send the mail because there was authentication from the source of the, certifying the source of the origin of those mails. So if you really want deniability in this kind of setting, you must use cryptographically deniable protocols. And this is what we have seen in the aftermath of the last US election. So we saw that the rate of usage of protocols like Signal jumped up like 400% because people saw that using email or using mechanisms like that is not inherently deniable. Okay? So now I'll hand over to Lachlan, who will tell you how deniable protocols work in practice.
Hi. So the traditional way of setting up a secure channel provides a kind of deniability in itself. So what you normally do is you do some kind of secure key establishment, and then after that you use symmetric crypto. And one of the features of this kind of symmetric authentication is that you use this kind of shared symmetric key, so in this case, kauth. Now, whoever is able to generate those tags, or whoever can verify those tags, sorry, they are also able to generate them. So if you can verify the authenticity of a message, that also gives you the ability to forge messages from that sender. And this is what makes this type of protocol somewhat deniable, because if Alice sends Bob a message using a protocol that's built like this, then the result is that if Bob tries to tell some verifier, so let's call the verifier Valerie, Bob tells Valerie that Alice said something, Valerie can't tell whether Bob is telling the truth or whether Bob just forged the message using his known information. So some concrete examples of this. Now, protocols have been designed that have deniability as a specific goal. So the OTR protocol, the off-the-record protocol, is perhaps the earliest example of this. So this takes the same kind of structure where you do an asymmetric key establishment and then you use symmetric crypto to authenticate individual messages. But now, once you've verified the authentication tag on a message, you release this MAC key. So you release this previous key that was used for verification. The result is that once this key has been released, anyone who's looking at these messages going over the wire, they can now forge authentication tags that look like they came from the sender. So this makes this kind of protocol, or makes this particular protocol, more deniable than if you use something like, say, TLS. And the result is it's easy to make transcripts that look realistic. So this protocol was around for quite a while, but in the last few years, the Signal protocol has become more popular. One of the reasons for that is that it works asynchronously, and so you don't need to have two people online to have a conversation. But a nice feature of this is that it is inherently significantly more deniable than protocols like OTR. So when you set up a Signal conversation, you set up you take a few different keys and you do some key exchanges to produce the session key. So you have a long-term identity key. So Alice has her own big A, but you also generate for each conversation an ephemeral key, in this case little a. And this is useful for forward secrecy, so that you can throw this away and then someone who compromises your long-term key can't read all your old messages. But what Signal does a bit differently is that they do this tripartite key exchange. So rather than do just a simple Diffie-Hellman key exchange, Alice does a Diffie-Hellman key exchange using her long-term key and Bob's short-term key, and between the short-term keys and so on. But the result is that you now need to have the private keys that you can use for all three of these Diffie-Hellman exchanges here. So you need to know the private key big A or little b. You also need to know either little a or big B, and you need to know one of the little a or little b. So from Alice's perspective, looking at this second line here, so Alice knows that she generated little a. She knows that she kept little a secret. So whoever she's talking to, whoever else knows this session key K, must know big B and therefore must be Bob. So this is where Signal gets its authentication from. But now let's look at deniability, because this key exchange has some helpful properties, and in particular anyone can forge the key exchange. So anyone can produce a completely legitimate looking transcript that claims to be from any two people without knowing any of their private keys, or without getting hold of any of their private keys. And it does this without compromising authentication. So how do we do this? So first we pick some private ephemeral keys, little a, little b. And this is fine, this doesn't need any special knowledge, because all you need to do is basically generate a random number. Now, you go to a key server. So in this case, because at Signal, they have their own server infrastructure set up so that you can look up someone's phone number and get a public key in return and various other things. So this is all either public information or something you can generate yourself. But notice that because you know little a and little b, and you know both of them, the situation is different from the case where there's a legitimate conversation between Alice and Bob. And the result is that you can now compute all three of these Diffie-Hellman components, because knowing both little a and little b is enough to compute each of these secrets. You can now generate this secret key K, and that lets you generate a whole Signal transcript that looks like it's really between Alice and Bob, but you can just make it yourself. So the result is that looking at a transcript like this of a Signal section, even if you now know all of the keys and you can verify that everything makes sense, it gives you no information on whether or not someone really said something. And so this takes us back to this idea that the easier it is to forge realistic-looking transcripts, the more deniable it is, because there's nothing here to tie Alice and Bob to a conversation. So now let's move forward to the attack. So our model here is that Alice and Bob are having some conversation with each other, and they're using a deniable messaging protocol. Now, the problem is Bob has some enemies, and they have the ability to hack into his device. And what they do is they hack into his device and either use a TEE on the device or steal his key, and they run the messaging program P. So at this point, nothing has changed except Bob's messaging client, so his Signal client in this case, but could be anything, that runs inside this TEE. Now, once this is done, we have that messaging client. We modify it a bit so that it produces a nice transcript of what was said, who said it, basically a nice record of evidence. But now, this is where the remote attestation comes in, because we can produce an attestation that says, this transcript that we've produced, this came from a TEE running program P. And program P, we can publish the source code, and it's implementing a Signal client. And so you can trust this, because if you trust this messaging protocol, then this means you should trust the results. And that means that Alice really did send whatever was in the transcript that has been put into the attestation. So the kind of trick here that happens is that a TEE lets you show how a piece of data, in this case a key, was used. So the traditional kind of view is that symmetric authentication means that anyone who is able to verify an authentication tag or who can verify that a message is legitimate, that gives them the ability to forge additional messages. But if you use a TEE to do your verification, then only this program P that's running in the TEE is able to use that key. So up to this point, perhaps there isn't an enormous change, but when remote attestation comes in, you can now prove to someone else that a verification operation was performed by this program P using the key, and that the key has been kept secret. So now, even though having the key gives you the ability to forge a transcript, you can prove that you've not forged anything, you can prove that you're telling the truth, and the result is that this authentication becomes transferable. So how we did this in practice, we used Signal in our particular case because it's popular, the protocol is used in a lot of places, the software architecture is kind of nice to work with, but any protocol will do except for some exotic ones that we'll talk about a little bit later. So we took this unofficial Signal CLI client, which contains all the normal stuff. So it contains some UI code, some network code, and then a cryptographic state machine. We then used an SGX enclave, which is a type of TEE that's in Intel processors since Skylake, I think around 2015. And we take the signal cryptographic library, implement it inside this TEE, and add some extra code that can do generation of the transcript and does the attestation. So we now connect this to the modified signal CLI client so that instead of using its own cryptographic state machine, it makes this external call and talks to an SGX enclave. And the result is this attested transcript. So it says the kind of things that you would expect in a transcript. It says, well, what's the identity key of the participants? What did they say? And then when you get to the end of the transcript, there's this remote attestation. And now someone who looks at this transcript and who can verify the remote attestation can then say, well, I know that this is a signal client. I know that it said, well, this came from Alice as identified by her identity key, and that it said this kind of something incriminating, or I did something embarrassing, or whatever. So now Alice is no longer able to deny what she said. So whoever broke into Bob's device can take this attestation, publish it on WikiLeaks, and anyone looking at it can be sure that it is something that was kind of legitimately stolen, rather than something that was just made up. So here's our demo. We've had some technical issues, so we've got a video here. So let's start. Thanks. So Bob runs his attack, and in this case we've got just a normal signal client running on an Android phone. And so he has his conversation with Alice. Now Alice sends whatever messages she wants to send. She can't tell the difference. She doesn't know that Bob is using this special client because she's just using the normal signal protocol. So she says whatever embarrassing thing she doesn't want to get out. And Bob, again, he's got a signal client. It's a bit modified, but it's still a signal client, and he sees these messages coming in. Now, at the end of their conversation, Bob will produce a transcript. And this transcript includes a remote attestation. And so it includes these messages that the verifier can then look at. So from the verifier's perspective, they load up this transcript, they put it into the program, and they can now see that Alice has apparently sent this message, say, "Hi Bob, I did something embarrassing." It shows her identity key, but now, because of the attestation, we can see that this particular program, so that had this particular hash of its code, which is what the MR enclave represents in the Intel system, that this particular piece of code produced this transcript. You can look at this code, make sure it is really an implementation of the signal protocol, and you can now be sure that these messages really were authenticated. So the result is you publish this transcript file on WikiLeaks, and now anyone who trusts that TEE and anyone who trusts the program on there, or the program source code, can verify that transcript and will be convinced that Alice really did send these messages. So now that we've done that, I'd like to move on to some countermeasures for this. Because while this will work with essentially any current messaging protocol, there are nonetheless some things that we can do to mitigate the problem. So first I'm going to talk about a class of protocols that is somewhat more resistant to this. But also there is another way that involves actually inserting remote attestation into the messaging protocol itself, essentially to show that you're not carrying out the attack. Finally, it's also possible to reduce the ability of someone to do this attack by essentially putting a human in the loop and making authentication depend on something that isn't attestable. So first I want to talk about online deniable protocols. So the deniability, as I spoke about before, it fails when you have a verifier that's interactive. So what we said before is that Alice sends Bob a message and then Bob can't prove anything after the fact. But what if this verifier, Valerie, is now talking to Bob at the same time? So the verifier is now actually involved in the messaging protocol itself. So what we can kind of do is imagine instead Bob lets the verifier take his place. So now instead of talking to Bob, Alice talks to Valerie. But there's a problem, which is that when you do this, because the protocol is authenticated, Alice knows she's talking to Valerie. Alice knows she isn't talking to Bob. So what the verifier does is asks Bob, well, I'm talking to Alice, but I don't want her to know that she is me. So can you just do something for me with your identity key to authenticate me to Alice? So Bob now does this, and Alice can, and this verifier can now be convinced that Alice has really said something. So what online deniable protocols do is they make forgery a little bit more easy, because now instead of the identity key just allowing you to set up a conversation, it also will allow you to man in the middle a conversation. So in the normal case, this is fine, because if you have your identity key, you keep it secret. So the only person who can man in the middle you is you. And, well, why would I attack myself? But with this kind of protocol, now if Bob tries to help this verifier to verify messages from Alice, that verifier doesn't know if Bob is actually using his identity key to help forge messages, or to try to forge messages from Alice. And so we're back in this original situation where Bob can forge messages that look like they're from Alice. The verifier has to depend on whether she trusts Bob. So we're back to the normal kind of deniability situation. So the upcoming OTR v4 protocol, which isn't ours, is going to be online deniable, and this is kind of a big thing for this particular protocol, and they were nice enough to acknowledge this attack as being an important justification for using this type of online deniable protocol. Now there are, however, limitations to this mitigation, because the attack is still possible if this identity key is created inside a TEE, like an SGX enclave. And the reason for this is that, like before, if a key is inside the TEE and you use attestation, then that lets you prove that you haven't used it to forge things. So as long as that identity key is the only thing that allows messages to be forged, if you protect it inside the TEE, then it's still possible to do this attack. But the result is that if you switch to an online deniable protocol, if you install a messaging app and create your identity keys, then someone who later on attacks you by compromising your mobile phone, say, they can no longer do this type of attack using attestation. So this is helpful in a really common case, though where it isn't useful is if the attacker is either able to compromise your device before you've installed the messaging app, or if Bob himself is the attacker and wants to do this kind of thing. So to protect against those kinds of attacks, we need to use something different. And in fact, we need to incorporate remote attestation into the messaging protocol itself. And the basic idea is that we use attestation to ensure, or to assure Alice that Bob he has a TEE, but that he isn't using it in a malicious way. So one thing that he can do, for example, is to try to show that a private key, it's not stored in a TEE, it's stored somewhere outside where the operating system can do whatever it wants with it. And the result is that the user, Bob, or whoever has compromised Bob's device, they can definitely forge messages. So they've proven that it's possible to produce forgeries of your messages. And so you can be certain that an attestation attack won't be convincing. So the downside of this is that it requires you don't protect your keys using a TEE, and this is bad because everyone wants to try to protect their keys. So an alternative is to try to implement the entire protocol inside one of these trusted execution environments and just don't do the attack. And you include in the protocol an attestation that says you're not carrying out this attack. So this lets you keep everything safe inside the TEE, and it reduces the ability of other software on your machine to decrypt messages, for example. But it has the downside that, as a countermeasure, it's less effective because you're attesting this huge piece of code, and whoever is receiving it, so Alice receiving this attestation from Bob, she needs to look at this huge program implementing a whole messaging client and be convinced that Bob isn't doing anything underhanded. And as a result, there is a trade-off in that the countermeasure can be more effective if you're willing to sacrifice the ability to use your trusted execution environment for good. So the final countermeasure that I'll talk about, which I've described as putting a human in the loop, depends on the fact that attestation can only convince someone else of what is actually verifiable on the machine. So if you have some kind of user input, for example, that isn't attestable because the hardware doesn't have any proof of what the human who is pressing the buttons is actually doing. So what you can do is, instead of having a long-term identity key that you use with everyone, you set up some kind of bilateral set of identity keys that's different for everyone you talk to, and the users have to verify fingerprints manually, which they have to do anyway, if you want to be kind of really secure. And so when you carry out the attack, you still get an attestation, you still get proof that some messages came from someone with a certain identity key, but what you don't get is proof that a particular person actually owns that key. And this, conveniently, is also compatible with current UIs. So this is Signal's UI for comparing identity keys. So you pull up this window on your Signal client, the person you're talking to also pulls this up, the number should be the same. And it's just a big opaque blob, and so if you no longer use a long-term identity key that's the same for everyone, it doesn't matter because this is an opaque blob, and you'll get a different kind of opaque blob, but it's still an opaque blob that will be the same on both of your phones. So, just a brief summary of these. So online deniable protocols, they're highly deployable because it's just a software change. And they're effective in at least some cases, and they're effective in the case where you're worried about someone coming in and compromising your device and publishing your messages online. So that's good, and that's important to a lot of people. But it's limited in that if an attacker takes hold of the device before the app is installed, then it doesn't help there. Now you can put remote attestation in, and that works very well in that it provides a very strong countermeasure, but it's difficult to deploy because remote attestation is difficult to use in end-user devices because there are so many different devices out there that you have to establish trust in, and so many software versions that are involved that it's perhaps not realistic to expect that messaging clients switch to this. So the last countermeasure that I talked about, where we essentially make authentication not verifiable completely on the machine, it's quite effective, and it doesn't require complicated changes, but it's very easy to get it wrong. Because, for example, if you have an authenticated key server lookup, so for example, you have a TLS connection where you send a message to the Signal server containing a phone number and it comes back with a public key. Well, now you have an authenticated linkage from this public key to a phone number, and they've lost their deniability. Because now there's this link, phone number, public key message. So as a result, we recommend switching to these online deniable protocols that are starting to become available. So, the big picture. First, it's not just messaging protocols. Anything that's machine verifiable will be at risk. So one perhaps positive use of this is that you can get a proof of anything that comes from a TLS server. And this might let you prove, for example, that a website has been distributing malware that's been perhaps targeted towards a specific person or that's coming intermittently through an ad network. But another kind of negative use is that in any kind of end-to-end verifiable voting system that doesn't involve some out-of-band thing like numbers on a paper card or something like that, you could then use attestation to prove that your vote was to a particular candidate, and that would allow things like vote selling and such. So.
Thanks, Lachlan. So we want to leave you with 3 thoughts. The first one is that I hope we have convinced you that deniability is important. This is evidenced by how popular protocols like Signals have become. But the more important thing is that the fact that attestation is now widely available doesn't give you the same guarantees that deniable protocols you thought would have given you, right? So this is important in 2 respects. If you're a developer and you were using a deniability mechanism, now you should realize that the assumptions that your protocol or your system was based on have changed because attestation is widely available. But more importantly, if you're a user who relied on deniability, if you are a whistleblower or if you're a dissident or somebody like that, and you were using a protocol like Signal or OTR or something like that, you should be aware that the level of deniability that you thought you had is not the same anymore, not because cryptographic deniability is broken. We haven't broken Signal, we haven't broken OTR, right? But the underlying assumptions have changed. And the silver lining is that there are protocols that can reduce this window of attack, such as the forthcoming OTR v4. So with that, thank you very much, and I hope we can still take a couple of questions. There's a question over there.
Just a general question. If I were to be chatting over WebRTC, for example, is it deniable or not?
Is WebRTC deniable?
WebRTC, I'm not familiar with how that particular protocol works, but does it provide some kind of authentication cryptographically, for example? Because if that's the case, then the attack will work.
From what I understand about WebRTC, the authentication is done by authentication provider that you choose. For example, it would be if you choose to have Facebook authenticate you for your browser, or Google or Mozilla or any one of those identity providers authenticate you, then they would help you establish the communication by passing the keys from you to the other person and the other person to you, and then you have a secure channel established between 2 browsers, and then you have the communication going. So that's how WebRTC works in principle. But yeah. So.
Okay, so I'll tentatively say that yes, that would work, because what you can then do is, so I'm, say, talking to Facebook and you have Google as your identity provider. So I use the attack on my connection to Facebook, and this whole process, I get an attestation to the fact that these keys are now shared with you. And then when I carry out the normal thing, I use the same attack, and that shows that this message or this call came from this particular channel, and because of that first attestation on the key exchange using these trusted parties, that then will link that back to the real-world identity.
So I guess another way of putting is that I don't know if WebRTC itself provides deniability, but if it does, this attack would be applicable because it shows one party's behavior as being correct by using attestation from that device.
Yeah. I mean, perhaps the kind of most straightforward way to put it is that if you have a protocol or if you have a system where on your screen you can come up with a person's name or long-term identity key that you don't have to kind of be involved with as a user, but just comes up on the screen, and if you can trust that.
We're out of time. Thank you very much, but we'll be here, so please come and ask questions. Thank you.
Thanks.